This was a water damage repair that probably shouldn't have happened. Let me go over why. So, as a lot of water damaged machines are, it came in for no backlight, which is pretty common and not that hard to fix. Usually it's just a part or two on the board or some water damage or a feedback via, maybe worst case scenario an LVD connector or a driver. In this case, it was everything, including the kitchen sink. The LVDS connector on the board was burnt, and usually when that happens, you could have problems with your screen. I checked the screen and it was shorted, so I had to replace the LVDS backlight, had to replace the fuse on the board, had to replace the screen. Then after I got all that together and working, I found out it had a bad battery. Then I replaced the battery, and then I found out it wasn't charging. And I went back and verified that the battery was also bad. It wasn't just that it wasn't charging. And I found out that I learned a lot about battery circuits thanks to this machine. And I found out it wasn't charging because of all things the SMC. I know that sounds out there, but it was the SMC. The SM bus SMC5G3 SCL signal was present, but it was weak and slightly distorted. And it wasn't solid enough for the communication to take place for it to activate the charging. So let's go over this circuit. And this machine probably should not have been fixed. It definitely wasn't worth the labor, but it was very educational. In my case, with this board, this data line from the SMC, this SCL line, the SMC was having a problem pulling this down. This is a pull-up resistor, and it was having a problem pulling it down. So the square waves, instead of looking like this, were just maybe a third of the way down and jiggly. It was not very clean. So the SMC did not have enough drive to properly overcome the 2K ohm pull-up resistor. And 2K is a lot of resistance. So if this chip can't pull 2K, obviously the drive circuitry that's trying to communicate and send that logic was damaged. So that's why I went ahead and changed the SMC. Even though there was no water damage around the SMC, everything else worked. Everything the SMC did was good, but these lines were damaged. Let's talk about how or why they could have been damaged. And unfortunately, with this type of a problem, you cannot see this with a voltmeter. It's impossible to see those pulses and to see the shape of those pulses and the condition of them with a voltmeter. So without an oscilloscope, this never would have been able to have been diagnosed. It would have been a shot in the dark. So the trickiness on this machine came when it was not charging. This is your battery connector right here. This is Q7155, which we'll go over in a minute. This is what's responsible for sending the voltage to charge the battery. Over here, this is U7100. This is the device, this is the chip that actually controls the battery charging. It also, it's responsible for a lot of jobs, but primarily it's going to run the battery and it's going to make sure that the 8 volts on the PP bus is present. And this obviously is the SMC, System Management Controller. This controls about everything. And this is actually what talks to the battery management system. So the battery is going to have its own electronics inside of it. It's going to have a BMS, a battery management system. So a lot of things have to work properly before you can charge a battery. First, the SMC has to talk to the battery and make sure that the battery is happy and okay and not in alarm mode, because the onboard battery management system on the battery itself is responsible for monitoring the battery's health and condition, and that reports to the SMC through a data line. Then once the SMC is happy, that the battery is happy, the SMC will tell U7100 to go ahead and charge the battery. U7100 then controls this gate on this FET right here, which controls this output voltage, which sends the voltage to the battery, and it monitors the current. And if the current's too high, it lowers the gate voltage here, or raises the gate voltage here in this case, which reduces the output current, which slows the charging down. So U7100 right here is going to regulate the charging of the battery through this FET using this resistor R7150. So let's go ahead and look at the schematics and see how this works. So let's start with the battery connector itself. As you can see, this is the SM bus, the SCLA and SDA. These are both serial communication lines. This is a bidirectional. This is going to be an input line. So this line is going to come from the SMC, and it's going to talk to the battery management controller. The battery management controller is going to talk back and forth on this bidirectional data line. These are merely surge protectors. These Zener are designed to protect in case there's a surge on these two lines. This is a pull down for system detect, so the charge controller knows that it's plugged in. And then we've got the negative and positive sides of the battery. So this is the one, this SM bus SCLA or SCL, this is the one that was damaged, and we'll go over that next. Here we can see we've got the SMC right here communicating to U7100, which is the charge controller for the battery, and the battery itself. So the battery system, the battery BMS, battery management system, the battery charger, which is the U7100 that we showed you earlier, and the SMC, all three use these data lines. The SM bus, the SMC5G3SCL data line, this one was damaged. These two are pull-up resistors, and their job is to merely pull these two data lines up to the PP3B42 hot, or the G3 hot level, which is basically pull the data lines up to 3.3 volts. And when the chips talk, they're going to pull the data lines down, and they will create square waves on the oscilloscope, and you'll be able to see the data go back and forth. So this is the data relationship for the battery management system. Okay, so here we have U7100, and this chip basically performs two functions. The main function of this chip is to basically create this rail here, which is your PP bus G3 hot rail. And so this takes your battery in, and this is going to create your main power rail. So besides creating your main power rail, there's a leg that comes off this main power rail right here, goes through this current sensing resistor, which basically U7100 monitors with these two resistors, and it measures the voltage drop to calculate current across this resistor. And then it turns on Q7155 to charge the battery. When there is no AC power, the battery power comes in through this Q7155, and as you can see, there's a diode here which will let the positive voltage flow through. It will go up, and that becomes your main power rail, your PP bus G3 hot power rail provided by the battery. When you're on AC, U7100 creates the PP bus directly through Q7130. So Q7155 is an incredibly simple circuit. If there is no power on the gate, it will not allow current to go through. But if there's power on the battery, because of this little diode right here, it will let the power go through regardless. In this case, the machine was not charging, and this was at 8 volts, preventing the PP bus from getting to the battery. So U7100 has a couple feedback lines. See this charger, CSO-RP and CSO-RN. Those are your two lines that it measures. They come in to U7100, and this is how U7100 is comfortable about the current going to the battery. So it's reading this right here, and it's going to watch that current, and it will adjust the gate of Q7155 accordingly to keep the amount of current in line so it safely charges the battery. And none of this will happen. It will not charge the battery unless Q7100 actually speaks to the SMC on these lines and gets the green light to actually start charging the battery and monitoring it. So the SMC is what's going to be talking to the battery management controller, and this is also on that same data set, and they all three have to be happy before it goes ahead and pulls this gate down and starts charging the battery. So now let's look at the data lines. Specifically, let's look at this SCL line from the SMC chip and see what those pulses should look like, so we know what we should be seeing from the SMC. And that is going to be right here. That's this one right here. Okay, so we're going to go ahead and look at the SM bus SCL signal, and we're going to go ahead and see what it looks like. And this is generated by the SMC. This is a one-way data line, and this is the SMC talking to the battery management controller. See it? There. Should be one more. There. So the SMC is sending these commands to the battery and trying to figure out what's going on, and that's how they're talking. And you can see that with an oscilloscope. You cannot see that with a voltmeter. You have to have an oscilloscope to see this chit chat. Let's go ahead and look at the SDA data line. This is a bidirectional data line. Let's see what it looks like. Saw a little activity there to start out with. Pretty quiet. The only chit chat going on this data line is when you initially give the unit power. So this data line is pretty quiet, and you can see that it's, oh, there's some activity. There, it's talking. Not quite as active as the SCA line, but you can definitely see there's some communication going on. And I can't tell you what this communication means. I have not looked at it close enough to understand who's talking to who. I can just simply observe that there is some communication going on. And this is the SDA data line. Okay, so let's take a look at the actual board and see where these devices are all at. So on the top side of these boards, you primarily have your larger power components. So this right here, see this chip right here? This is your Q7155. This side is your drain right here. These top three, 1, 2, 3, are your source, and this is your gate. This is your battery connector. These are your hot sides. These are your ground sides. And these are your battery data lines where it's talking. The SM bus, SMC, SDA, and SCL lines are going to be right here. We flip the board over, and here we're going to find U7100. Right here we're going to find those two resistors are 7151 and 7152 that it's using to measure the current drop. On this resistor, which I forgot to mention earlier, right here, this is R7150. This is your resistor that Q71 or U7100 is using to measure the current that this is taking through the source to the drain, and it controls it on the gate. Now, if you look at this particular chip, the Q7155, this gate When high, stops the current flow. When low, allows the current flow. And this gate is not pulsed, it's a voltage that goes up and down, which is controlled by U7100, which has got a feedback loop which monitors the voltage, which is its way of seeing the current that goes through that chip. And this is your SMC, your System Management Controller. And let's see if we can look in here a little closer to see the SCL line on this chip. It's going to be right there. There's your data line that's coming from this chip on this resistor here. This is the pull-up resistor, and this is how this chip through this leg right here talks to the battery. So that's the parts on the board. So let's look at what the readings should be. So if the battery is not charging at all, this gate will be at a full 8 volts, full PP bus voltage, and this will not allow current to go through. If this is pulled down, it allows current to go through. So let's look at the gate voltage on the oscilloscope. This can be read with a voltmeter, okay, but it's not. You can see it on the scope as well, and I have the scope out already, so let's look at that. Okay, so let's go ahead and watch the gate. And basically how the gate works is if it's at 8 volts, it's not allowing any current to go through. And 8 volts on this, because each one of these squares is 5 volts, 8 volts is going to be about right here. So the line should jump up to about 8 volts, and then as charging is enabled, it should drop back down to the low level, which is allowing the voltage to go through. So let's go ahead and watch that. Got my probe on the gate. It's fired up. There it goes up and comes down. And now it obviously is charging. Just to confirm that, let's look on the output. And there you go. Looks like 5, 6, 7 volts there. So the output's about 7 volts. And let's look at it with the power disconnected. And there you go. That kind of shows you the voltage of the battery. There's no power on the board anymore. So you can see at 5 volts per division, the battery isn't even making 5 volts, it's 2 volts. So the battery is basically dead. It needs charged. So this is testing with a battery that is basically dead, so you can see how it works. Now let's go ahead and let's take a look at a battery that's fully charged so you can see the difference. Okay, so I've switched batteries. This battery that's on here I know is good, and it is completely charged up. So before we hook up power, let's go ahead and look at the drain, and let's see what the voltage is. And we can see the voltage is 8 volts. It's almost all the way up right there, because these are 5 volts per division. You can see we're pretty much all the way full, a little over 8 volts there. So the battery is completely charged, as you can see. So let's go ahead and apply power and see what it does. First, we're going to look at the drain, and we probably won't see much of a change here because the battery is fully charged. So let's apply power. And we don't see much of a change at all. So let's go ahead and let's look at the gate, and let's see how the gate behaves on a fully charged battery. As you can see, it goes up and doesn't come back down because it's detected that the battery is completely charged. Let's do that one more time. I have to unplug the battery and plug it back in because the board is running. So let's go ahead and get on the gate right now. And the gate's going to be, it's a little up there. That's because the battery is now plugged in and it's running PP3B42 and it's turned on a couple rails. So there's just some stray voltage there. Let's go ahead and apply power to the board now. As you can see, the voltage goes up and doesn't come back down. And the reason it's not coming back down is because the battery stated charge is 100% and it doesn't need any current. So the U7100 is not opening up the gate on Q7155, so it is currently not charging. Just for fun, let's look at our data. I'm going to go ahead and look at the SDA line. This pin 4 of J6950. And because I've got the battery plugged in, you see how that's already at 342. That's because the SMC is running and the pull-up resistor is already active. So as long as the battery has enough power to run the SMC, that pull-up resistor is there. So let's go ahead and put some power on it. There. See the data line activity? See that? I don't have it at 2 volts for division, I have it on 5, so it's not as large as you saw in the other videos. But that is a normally functioning battery charging circuit. So when you test these battery charging circuits, there's more than just what's the voltage. You have to make sure the data is getting there and the data is clean and it's what it's supposed to be. And that's how you determine whether you got a problem with Q7155, whether you got a problem with the SMC, whether you got a problem with U7100, whether you got a damage or one of the current sensing resistors. That is basically the battery circuit in a nutshell.